Welcome back to the ChemDoctor, and this video goes out to everybody in the United States who's really cold today, I guess in the northeast part of our country, and I'm here in Phoenix and it's raining today. I guess we got it easiest of everybody, and then specifically to those hardworking general chem students who are in their first semester up in Flagstaff at NAU. So here, what we're going to do in this video is continue on doing calculations with thermochemical equations. And in this case, what we're going to do is we're going to say that we've got 100 grams of oxygen, and what we want to know is how much energy is going to be released from this reaction when all 100 grams of the oxygen reacts with an excess of propane. All right, so let me just write that in there. We have an excess of propane. We have 100 grams of O2. In the previous videos, I've utilized this equation, and I want to point out the reason that I have added the energy released from this reaction to the product side of the reaction is because this particular reaction is exothermic, and we get that information because generally speaking, when this is presented to you, the balanced equation will be here, and followed by that will be the delta H, or the change in enthalpy per mole of that particular chemical reaction. You'll notice that there's a negative sign here. That means that this reaction is exothermic and it releases energy, this value of energy, based on per mole of balanced equation. What that means, and I want to remind the viewer of that, what that means is that when 1 mole of propane combusts with 5 moles of oxygen and the reaction goes to completion producing 3 moles of carbon dioxide and 4 moles of H2O, then 2,221 kilojoules of energy is released. So we can treat this energy value as if it's a product, and its coefficient here would be a 1. All right? So 1 mole of propane reacts with 5 moles of oxygen to produce 3 moles of CO2, 4 moles of H2O, and 2,221 kilojoules of energy. All right? So we can treat the energy value for an exothermic reaction as if it is a product in that balanced chemical equation. So the question is, we want to know what fraction of energy is now going to be released when instead of 5 moles of O2, we burn 100 grams of it. So you treat this problem as if it was a theoretical yield problem. So the first thing we're going to do is we're going to pull down the mass of the O2, and we're going to find the moles. So we're going to use unit multiplier method to do that, therefore we're going to divide the 100 grams of O2 by 32 grams. Unit multiplier method, this is what this looks like. So we have grams of canceling with grams, and we've solved for the moles of O2. All right, and the moles of O2 in 100 grams is going to be about 3.125 moles of O2. So you see that we do not have 5 moles here. Now, once we have the moles of O2, how do we figure out the energy budget on this thing? Well, remember that the energy that's released here is based on the balanced equation. So the 2,221 kilojoules of energy that's released is based on 5 moles of O2. So to find the per mole value of energy released for oxygen, all right, so energy released for oxygen, this is going to be 2,221 kilojoules of energy per 5 mole of O2, which is equal to, and I'm going to go ahead and bring back my negative sign to be clear that this energy is going to be released. So it's going to be minus 444.2 kilojoules of energy released now per mole of O2. So now we have the energy released, or the energy budget for this particular reaction, in a per mole value on the O2. So now we're ready to combine these two values together. All right, this guy here and this guy here to find the energy that's released when we burn 3.125 moles of O2 with C3H8. And actually, the way I said that is not exactly accurate because it's not the oxygen burning, it's the propane that's burning, all right? But in any case, so let's figure this out. So we're going to have 3.125 mole of O2, all right? And we want our energy, so this is going to be times negative 444.2 kilojoules of energy per mole of O2. You can see how the moles of O2 are going to now cancel out, and we get the total energy that's going to be released from this, which is going to be about minus 1,388.2 kilojoules of energy. Okay, when 3.125 moles of O2 are combusted with the C3H8. All right. Now, to introduce Hess's law for the next problem that we're going to work on in the next video, what I want to do is start talking about how this stuff works. So, if we look at the energy diagram for this reaction. All right, this is what it's going to look like. All right, so we have our reactant starting in an arbitrary location, and then they're going to finish like this. And I'll designate the reactants this way, which would be the propane and the oxygen, and my products here, which are going to be the CO2 and the H2O. And I'm noting that H1, the energy of the reactants, is here. And we can draw a line over to where the products are, and the energy of the products are here. If I bring this baby out like that, then the energy difference is going to be equal to H2 minus H1. So now, to introduce Hess's law, if we want to reverse this reaction, basically we're going to start here at the products. All right, and we're going to walk backwards to the reactants. So if I'm going to reverse my reaction, I'm going to rewrite it. All right, where we've got 3 CO2s plus 4 H2Os going to 1 C3H8, and I've got a gap here for a reason, you'll see in a minute, and then plus 5 O2s. Now, when we walk backwards, note what's happening. We're starting at a lower potential energy with the products, and we're finishing at a higher potential energy at the reactants. So in essence, when we reverse a reaction, we literally are going to have to put back into the system the same amount of energy that was released. We have to climb back up this energy gap to the point where we started. So the value in energy, the magnitude of it, this distance in here is not changing. We will flip the sign because now, instead of releasing energy, you would have to absorb energy to go in reverse. We would have to essentially, if you were standing next to this process once we reverse it, you would feel suddenly as if the area around you was cooling down. And that's because that energy is going to have to be used to build up the reactants back to a higher potential energy. So what we can do here in the way I wrote this reaction is we can put the energy value now. Remember, instead of being a product, now this thing is a reactant. So we can actually write it in here like we did as we represented it when we were considering this reaction as energy was being released. So in this case now, the energy is acting as a reactant. Why? Because we've got to take these two reactants and we have to push them back up to a higher potential energy. All right, and with that, I'm going to go ahead and close this video.